All right, it's back. This problem has returned. So I have thoughts. I have thoughts on how to solve this, and I also have a little bit of an explanation of one of the ideas I have how to solve it and why and how it might work. So I'm going to see if I can do this, and I'm going to see if I can get it. So basically, as of... Okay, I'm going to delete this. I don't see this coming in. Now, the second I delete it, I guarantee it will come in useful, so I'm not going to do it. Okay, so yesterday I was... Actually, let's put these back. Yesterday I was trialing these different functions and seeing how they were going to turn out. And you can see with this one, I'll end up cancelling the x squareds, cancelling the y squareds, and I'm going to be left with this. And I can tell by looking at this, I'm fairly certain I'm fairly certain I went through and tested this, and this was not equal to 0. I don't think I can tell just by looking at it, but I'm fairly certain I went through and tested. Did I test this last night? I don't remember. I must have done, because I did rule it out. I just hope I didn't rule it out right from this stage, because that would be a little bit bad. We'd have, what, a 3w squared. We'd have a 2yw plus y squared plus, 2xw plus x squared. Yeah, okay, I'm now just doing this. This was not what I intended on. But, so I have had some... I'm going to go through this. But yes, I have had some thoughts on how potentially to solve this. There were... Or, yes, on methods that I might be able to use. I'm just going to expand out this bracket. This bracket that you have seen me expand out a million times. Or at least if you watched the previous one. If you have not watched the previous one, this will probably make no sense, and you're probably wondering why I've randomly started doing maths on a video. I mean, in fairness, even if you watched the last one, you're still probably wondering why I randomly started doing maths in a video. And then you might remember the name of this channel is Ninja Warlog, because it's here for me to do whatever the heck I like / random thing springs to mind. So... yeah, this is why I have this channel, so stuff like this doesn't go on the main channel. Yeah, okay, and then we get, this is the bit where we get 4xy, because we always get 4xy, and the other two terms cancel. 4xy. Again, that was just a bit of maths that I did so much yesterday, it became drilled into my brain, and I think, oh no, this isn't quite sufficient yet. I do remember how this didn't work last time, but I might as well go through. Oh, I guess I didn't actually do it this way around. This is a potentially more interesting way of doing it. So, or it might be a little bit more obvious why stuff will / won't work. Or it might work and it turns out I just discarded it early last night, but I'm fairly certain I didn't. Although I don't like how close this is looking. So again, cancel this, expand that, pull the y inside this bracket, drop there, expand out the bracket, because there's now no reason to keep it around. I'm going to get rid of that sign. I'm now going to pull this x inside here, get an xy, it's going to be a minus sign there, because we're going to just expand that out to that. I'm not bothering putting there. So there are things I do whilst doing these because I do write maths in Word a lot of the time. I've gotten used to pulling tricks that make it go faster. Okay, so yes. Why it's not going to work. Going to be these xy terms. They're not going to cancel. So you can see the y squares will cancel. Y squared cancels. The x squared is going to cancel with this x squared. What will happen with these terms? Okay. So we're going to have the following things left over. I'm going to pull this together with that, 2xy. That will partially cancel, won't entirely cancel with that. And I'm going to have an x plus y by pulling these two terms together. What I should do, and what I haven't done, is close the huge other word tab I have open at the moment. Because that probably isn't doing anything for the speed of this thing. Yeah, you can see that saving at the bottom there, probably. I'm glad it didn't say the file location to which it was saving, but that would have doxed me. Not that I think anyone cares that much, but... So this actually comes quite close. This actually comes really close. Which is quite interesting. So I'm going to try next f of x, y. So, okay, yeah, let's just go through what this comes out to be. This comes out to be 3. This is going to be, I'm just multiplying 3 over 4 inside this bracket. So that's going to come out to be 3 over 2. And this is also going to come out to be 3 over 2. I'm going to delete this. And we can now compare terms. And you can see we're really close to everything cancelling and to this being equal to 0. And we know that if this is equal to 0, because the way I got this was substituting into the defining relationship up there for f, x, and y. Or at least that's probably how I arrived at this. Because I am just working off of last night's stuff. But I'm a little bit less tired now than I was last night, which means I'm more likely to spot stuff that might be useful. And so what I'm, for instance, spotting is the fact that factors, we seem to be really close. Some interesting, that y should have been deleted earlier. We seem to be really close to some interesting factors. Because, yes, this is going to go down to a half of that. And both of these terms were cross terms that we potentially could have gotten rid of. And they came up in the proportion 2 to 1 as they are at the moment. So I think a solution that gets rid of this, I don't think it's going to be that. Well, I know that one didn't work. So I'm going to try something very, very similar, and I will have to duplicate a lot of work again. I'm trying to keep this, normally when I do stuff, when I do maths, hard maths problems, or it's typically physics, but it degenerates into hard maths fairly quickly most of the time. Normally I will do everything on one document, so I don't, or just keep going down every time I come up with a new attempt, so I don't lose stuff. But here I'm trying to keep it reasonably succinct. I'm trying to keep it so like most of it's visible at every point in time. Okay, so what are we going to do? I'm going to substitute this in. For anyone who is new to this problem, this was a problem I was set last night, and thinking I knew how to solve it, thinking I'd seen the trick, I sat down to solve it right before I went to bed, and an hour and a half later, I eventually conceded that I did not have a good way of solving this problem. And near the end, I was fairly convinced it was something quadratic in form, and so suggested I might try this. If I try this, I'm probably going to plug it into Mathematica to give me a solution. I wasn't presented this problem with any limits on what form of solution software I was and was not allowed to use, so I definitely would plug that into Mathematica because I don't want to have to do all that myself. And get a solution. Okay, and so we can begin by cancelling out the obvious terms, and this will get us to almost exactly where we were before, except we'll have an extra factor of a we can substitute in and play with. Incidentally, well, actually no, I'm not going to just do this. I'm going to add in a plus c. And that's going to get us a plus 2c on this side, because we had two terms with f of x, y in it. I'm going to cancel, and we'll just be left with a plus C there. I'm adding this in because I suspect it will come up in the solution. In fact, C will be the answer if this form of an equation does work. And yeah, that would be, if that does work, it'll be lovely. I'm then going to just cancel down the obvious terms. So we've got an AX squared on both sides, so I'm going to delete that. And we are going to have an AY squared on both sides, so I'm going to delete that. And this gets us basically to where we were before. I'm now going to go through the same process of expanding out something you literally just saw me expand out. I really should just write down these common expansions. So let's actually do that now, because this would have been such a great thing to have written. Like, I don't need any of this stuff that's up above. I probably won't anyway. I'm scared I will, so I'm not deleting it, but something that I definitely will need, and that will come up again, is W squared. And I've not written this down anywhere, so let's write this down quickly. So I'm going to be squaring this. Let's first off take out the quarter we know we're going to get out from the denominator. And I'm going to copy and paste this. Again, yeah, I've done this one so many times, but I still haven't memorized the answer, because I don't have that good a memory, it would appear. So delete that. Two minus signs cancel. Get rid of that. We're going to have the same term coming out from this side, just with 2 in the front, because that's how quadratics work. And I'm then going to get that term squared coming out as the final term. Substitute it in. We know these terms are going to cancel to get us 4xy. Okay, and we're left with this. And I will probably move the half inside. And this is a good thing to have on hand. Another good thing to have on hand is going to be... I'm debating what I do. I mean, y plus w on its own is easy. I'm going to do y plus w squared, because that seems likely to come up a lot. Okay, so, well, and x plus w. But one nice thing is we can note the symmetry in x and y, and know that, or the symmetry under interchange of x and y, that they basically look exactly... they basically end up looking exactly the same. Because, yeah, in all of the equations, you can swap x and y, and the equation says exactly the same thing, because everything commutes, which is lovely, which means at the very least solutions to this equation must be commutative. So if there either exists a single solution, or there exist multiple solutions, but you can interchange x and y in them, and yeah, you'll get something out. Okay, so do this. I'm going to go through exactly the same process, except this time I'm going to pull this y up there, and that will result in a minus sign there. And again, pull out the quarter in advance, just to really cut down on the number of terms we're working with. And do I want to... I'm going to expand it out. I could do the, oh, there, it's something squared, so I get the 2 of the thing, and I will end up doing something that's equivalent to that, but I find it easier just to keep track of every term I have if I do something like this. It's going to be twice that, and then it's going to be this squared, which is just that. And this is our expansion. That cancels. This is obviously just that squared. Okay, and so that actually just entirely cancels. Did I muck that up earlier? Okay, let's just keep going. Oh, I know. Okay, no, I'm going to do this. I'm not going to work that out, because I don't need to work it out here. And I'm going to try and keep to, because I thought I saw something the last time I did this, I'm going to just try and keep to as familiar territory as I possibly can. Basically, I'm just scared that the idea I've had won't work. And so in order to do as much as I can about that, I'm going to... well, it kind of helps, because if the idea I had doesn't work, it helps to see why it doesn't work. Like, if I had the idea because I followed a particular method, it's a good idea to, if I think that idea won't work, to go back and follow the same method again, so that I can see exactly where it failed. Okay, so we're going to have 2a plus 1 w squared. And that's going to get rid of these. And was it a case... No, it wasn't quite okay. Okay. I thought I might have messed up quite badly there, but I don't think I have just yet. I mean, I'm sure I have, but not in this particular instance. So I'm going to substitute in w squared. Now that we have that, I'm going to move the w squared to a far more prestigious place, because it does not deserve to be at the bottom of this list. It's possibly one of the most useful formulae I've actually written out at any point here. Go with there. I think that's where it deserves to be. And I'm then going to substitute in w, which arguably isn't the most important formula, probably is the second most important. Substitute this in there. And yeah, so we can see this is still going to cancel our x squareds and our y squareds, which is good. That's what I'm hoping for. That's what I'm kind of relying on with this. And then the x is going to be multiplied through by these terms. And we can then see, okay, the x and the minus x are going to cancel, or the x squared, and let's just write it out to just be clear what it is I'm doing. So it's going to be minus xy. Bring that through. We get that. Those two cancel. Okay, I'm going to do the same thing here. That's not what I meant to do. That's what I meant to do. Okay, same thing here, and I'm going to, again, pull the y inside all of these brackets. Get a y squared. Get a y out the front of that. There. Okay. So this is good. So again, get it now expand out the negative. Take this there. Delete the repeated y squared. Okay. And now we're at quite a nice place. This was where I hoped we'd get to. I still need a little bit of luck for this to work. A little bit of luck, or a little bit of this problem being set up in such a way that it does work. So what I'm now going to do is collect every term in xy. Collect every... So yeah, what I'm just going to do is I'm going to say that in order for this to be equal for all values of x and y, I need all these xy terms to cancel, and I need all of these terms to cancel, and I'm going to need this constant term to also cancel, and I'm just going to split this up into three separate equations. So I'm going to go 2a xy plus, so I'm going to take the xy term from this, and it's going to be minus a xy, and we're going to have two of those because we get one from that, and this must be equal to 0, so we're saying that all of those terms combined sum to 0, because remember we want this whole thing to be equal to 0. So the coefficients on all of them must go to 0. And even from that term, we can see this doesn't quite work, which is annoying. Because that 2a is going to cancel. So we can get really close with this. I can get here up to a factor of xy. That's this xy is going to be that one factor I can't get rid of. But I will be able to get rid of everything else, which is a good sign. So okay, so a little bit of a backtrack given. So this idea comes very close, but we end up having I can find values of a and c. I've got enough degrees of freedom in the problem that I can find values of a and c almost. Well, let's do this actually. Let's show that I can do it rather than just stating we have enough degrees of freedom and leaving it at that. So I'm going to take this term. By that, I'm going to add on the a times this. And I'm going to add on the a times this. Okay, and we're going to set all of this equal to 0. Let's rearrange quickly. So, well, for starters, we can note that we've got an x plus y here, which was what I was relying on. because that x plus y then means that we can divide this entire thing through by this term, because we've got that, our only terms in x and y occur there and there. We can divide it through, or equivalently factor it out, because we are evaluating this at x and y equals 0, but I'm saying that this holds true everywhere, not just at one place. That's what I'm attempting to solve. And again, we get this equation. So this is seeming too kind of nicely coincidental that none of this is working, which is quite interesting. Almost as though this problem was set up to be difficult. I guess I can substitute this in here. I just assumed this would work. I'm glad I checked now, because it doesn't work. This does not, again, give us enough degrees of freedom to solve the problem. Now, this must have been what I came to last night, except I didn't have this factor of a in here. Because then what's going to happen is, well, I've got 2a over 2, or minus 2a over 2, plus a, that's 0. So we're going to get rid of that. And we have another statement that isn't true. We can see we have a statement that isn't true up here, which means there is nothing of this form that will work. But it's interesting how close we get. And it's interesting that that cancels both times. This almost feels like... So here's something really, really interesting. If I can solve this for any equation that has an ax squared plus y squared in it, which, bear in mind, even an equation that doesn't have that does have it in, but with that set to 0. Any equation that has that in it must necessarily end up with these same terms remaining. Therefore, any complete equation, including these, that does work for f of x and y, must cancel those two terms, somehow. But if it can cancel those two terms... Wait a second. Okay, yeah, I'm sorry, I'm distracting myself. Yes, if it can cancel those two terms, then it will cancel them for any value of a, and therefore no matter what a I put in here, I will always get an answer, which works, at least for some c. But that's really interesting, because that tells us that no matter what solution I have... Is this a non-uniqueness proof? I think this is a non-uniqueness proof. I think I may have just proven there is no unique answer to this problem. Because let's go back and look at all the conditions I had, and specifically look at where the conditions came from. So, well, they came from expanding out these. And when I expanded out these, I had the following. So this is equal to... So I had all my xy terms just gave me a single xy. And it's going to be a positive because it's just this xy term, because the a's cancel. And all of these other terms are going to give me this. Sorry, yeah, all of the other, so okay, all of the terms involving this, we're going to find what we found a second ago, which is that only the terms that don't have an a in them, that basically that we get the same answer no matter what a is, therefore we can set a to 0, and we're going to see we only get this term coming out. And we're going to have this plus, and then we're just going to have plus the following. 2a plus 1 divided by 2 plus c. Now, this whole thing does not equal 0. Oh, this isn't a non-uniqueness proof. But This is a solution. This is a completely accidental route to a solution. I think this... Maybe this... Oh, no, maybe this doesn't quite work. I'm not certain. Okay, but notice... So, okay, this was what? Yeah, so any solution I can write in the form... I can write in the following form. F of xy is equal to g of xy plus this. All right. Now, no, this is a non-uniqueness proof. Now, let us say that we know the answer. Let us say we have found g such that this initial formula holds. G is equal to... this is not the same g as I'm using up above. Let's say we found g such that... I'm just going to delete all references to g. There was no g that ever existed in the past. You saw nothing. In fact, no, I'm not going to delete more stuff, but just because I'm still very scared I might need it. But I'm fairly certain this proof holds. So let us now say that we have a solution g such that this holds. I can now show this must hold. Oh no, does this quite work? So, okay. This doesn't. I don't think this quite works, actually. But it's close. Okay, so the argument goes... This is still a good argument to run through because it might get us closer to the answer. So I can say that, okay, we know... We're going to know any solution to this equation because the following statement will be true. This minus this equals 0. Now, let's substitute f of x, and so we can define some function, let's call it h, it's actually a function, it's a functional, I don't know, I'm going to call it functional. I'm going to define, it's not a functional, I'm going to define h of g of x, comma y, I guess, h of g of x and y to be, for some arbitrary function g, I guess I shouldn't have used g because we've already defined that, some arbitrary function k, I'm going to define it to be this. One second. Yes, so I'm going to define it. I'm going to define it to be this. Now, I can say that for any function that is a solution to this equation, that this is equal to 0. And so I can test any function. If this does equal 0, then that's our solution. So what I'm now going to do is I'm now going to test f. So assuming g is a solution, which means g obeys this equation, I'm going to test f. I'm going to find what happens when I substitute f into this. So I'm going to substitute f for k. And, wow, this is... yeah, so I'm just going to... Let's just copy in this. Let's put in f. Okay, so we're going to work this out. And now what happens when I actually substitute what f is. Let's do this. So I'm now going to replace every x with an x plus w, or every x in this part. W is going to be x plus w. And then I'm going to do the same here. So I'm going to copy this down, substitute in a y plus w. Okay, and I forgot to keep track of the minus sign when I expanded that out, because there should be that minus sign there, but I just didn't keep track of that when I expanded those brackets, so I'm now going to cancel this c with this, so we're going to be left with just a plus c at the very end of our equation. Okay, now we're going to note that we've already defined this as working for g. So we're assuming g is a solution, and therefore I can delete all of that. We're then left with this. I don't want to have to show this completely, because this is exactly the maths I just went through. But I'm going to cancel out these x's and y's with those in here. And, okay, so this didn't end up being equal to 0, but this was this same equation that we had down here. And what did that end up being equal to? It ended up being equal to this. But this is true for any value of a, including when a equals 0. So if we just add a constant onto... So, yeah. Or including, I guess, just when this last term cancels. So under what condition is this last term going to cancel? It's going to cancel when this is equal to 0. It's going to be minus c, b minus 2c. I guess, actually, it will just cancel. That's pointless. I don't need to do any of that. It will just cancel when c is equal to minus this. And so, I don't know if we've actually made any progress. But I can substitute this back in. That's going to get us to this. There are a couple of pieces of progress I think we might have made here, though. Some which are less obvious than others. And that's going to be a plus a half. Okay, and but... Wait a second, why did I do that? That was not what I intended on. Okay, we'll just pretend none of that happened. And I then drop this in. So what did I hope this would get me? I hoped to be able to argue something about when a is equal to 0. Because when a is equal to 0, well, because we can rewrite this as this. And we can then set a equal to 0, which gives me the following. And we know that when we put, so we can say that when we can say that we can define f of x such that this is true. If we do define f of x in that way, we get this. I don't know if this gives us useful information. I was really hoping it would. If I'm honest. Maybe it still does. Maybe it doesn't. It's not going to because the G's are going to cancel. Unless... Let's see what happens if we do substitute this in. This might arrive at a contradiction. I think it does. Does this state that this problem is inconsistent? So I'm going to work out the h of this. It's going to be given by that. I can then do -1 or -half plus a half, because we've also got that term in here. Two of those are going to cancel. Cancel to give that. We know by definition that all of the G's cancel. Which gives this. And that's not a contradiction insofar as it... Wait a second. No. Let's... Yes, that is right. And that is allegedly equal to this. But those are two different functions. This should be true for every single value. So I think that's a contradiction. I think that states that there is no unique solution to this. That no function exists such that this is true. Or at the very least, that no single valued function exists such that this is true. I can imagine there being multi-valued functions for which this works. But I think that's a disproof. It's not what I was asked to do. I was challenged to find f of 0, 0. But I think I can prove that there is no single valued solution to this problem. And therefore the f of 0 to 0 could be multiple things. I feel like I've proven there is no solution to this formula. Or no solution which holds everywhere. So I'm going to delete most of this stuff and go back up to the very start and try and be very, very clear and very, very explicit as to why I think that there exists no solution to this problem. Okay, so I'm going to have this on hand so I can pull previous formulae that I've basically, so I don't forget where I'm going and so I can pull out this w squared when I need to. So let's go. First off, I'm going to define the function h of f of xy to be equal to this minus this. Okay, I'm now going to find the h value of a particular function, which will come in handy later. So I'm going to define the h value of a x squared plus y squared. And this is going to be equal to w squared, which is why I wanted to keep that on hand. It's going to be equal to Actually, do I want to do this in this order? Yeah, let's do it in this order for now. Yeah, I think this is fine. Okay, so I'm going to, let's equal, so I'm going to substitute this in, so this is y plus w. I'm going to do the same thing again, except this time x plus w. And then I'm going to do the same thing again, except I'm going to subtract this term, and that's just going to be an x squared. This step follows. We can then rewrite and cancel this term. So I'm going to first cancel out the x squared and y squared. To those here and here, such that we are left with this term. I'm then going to, I'm going to expand out this. So I'm going to take w squared plus 2yw plus y squared. And at the same time, I'm going to do x squared plus 2xw plus w squared. Okay, and I'm now going to just take the terms that have a w squared, and then I'm going to pull them all together. So I'm going to expand out these brackets. Let's do it to be clear. Expand out brackets. Going to chuck an a here, an a here, and an a here. All those there. Those here, and then we're going to pull all of the a's together, so that's going to be 2a plus 1 w squared. Okay, and I'm gonna, do I want to pull those two terms together? I'm not going to for now, so I'm now going to substitute in the definition of w into those two equations there. I'm going to cancel 2's, I'm going to copy this there, okay, and again gonna cancel the 2's. Okay, I'm going to expand this out, drop those terms in here, and I'm going to do the same up top. So I'll drop these terms. If you're noticing, this is exactly the same thing I did before. Yep. I've done this. I've done this and things like this now so many times. So I'm going to expand into these brackets. So I mark that up. There we are. It's better. I'm going to expand into this bracket. It's going to be an ax squared. It's going to be an axy. Okay, so this is all good, and you can see these two terms cancel. They're quite neatly positioned to show that, and we can see this term cancels with this term. So those cancel. However, there are still some terms which do not cancel. So we can pull those all together into one big term, or not one big term, two terms, I guess. It's going to be equal to that, and we're going to have x plus y. This. Okay, and with that out of the way, I can chuck in our definition of w squared, which we calculated earlier. Do I want to do this again? I really, really cannot stress how much I don't want to do this again, so I'm not going to. I've calculated that value of w squared so many times. Okay, and I'm then going to note some things. So actually, I'm going to split this term up first. I'm going to paste this in here 3 times. That's not what has happened. There we are. Paste this term in here 3 times, and we can now pair terms off. So we can consider this term. That's 2axy. That is going to cancel with the 2axy over here. to just give us xy. And we can do the same. Wait a second, have I messed up somewhere? I have. Definitely have messed up somewhere. Where have I messed up? Oh no, I haven't. I need to trust myself. Okay, where was I? Yes, I was... What was the last thing I did? Yes, so I cancelled that. Okay, yeah. Back to trusting myself. Okay, so we notice we have a... Let's pull this up on top of this here. A 2a over 2. Okay, so I'm going to take the 2's in there. Substitute. And that's obviously just 2. So we can then see that this term is going to cancel. Well, that term is going to cancel with this term because they're both same contents inside there, but they've just got an A in front of them. So we're going to take the A, take that A. We're going to cancel both of them. And we're going to get the following. Okay, and I could have also done this. So we can show relatively quickly that this plus C, because I forgot to do this, but let's show it now quickly. So this plus C is going to be, well, we're going to check a plus C every time we have an f of x. It's plus C, and that's going to be a minus C. So this plus C, those two are going to cancel. And we're going to be left with just this plus C, which I will write at the end for convenience sake. And therefore, anything plus C is going to go to, well, this is equal to h of that plus C. But the plus C comes out. So plus a constant, note it has to be a constant, but plus any constant, we get to this, which tells us the following. Tells us that this plus C is equal to this plus C. And what I can then do, yeah, let's do it. I wouldn't need to do this at some point. Actually, don't want to do this right now. Don't think I do. What I want to do next is to consider how do I want to go about this? Okay, yeah, let's consider this. Still isn't the neatest way I could possibly run through this, but I think it's going to work. So I'm going to try the same thing again. Okay, so I'm going to say, assume that we have a solution, g of x and y, such that it solves our problem. And what we're going to show, so this is by definition a function which solves our problem. We are assuming that such a function exists. Now what we are going to do is to show that the very assumption that such a function exists directly leads to a contradiction. So in other words, if this function exists, that directly implies something that is not true. Therefore, that function cannot exist. We have a statement which proves a statement to be false, which proves a statement that is false to be true. Therefore, the statement you started with must itself be false, because otherwise the false statement you just proved would be true, but we know it isn't because it's false. So we want to use this assumption, and we want to show that assuming a function such as g of x and y exists directly proves a contradiction. So I'm going to take this. I'm going to take g of x, y. I am then going... No, well, yeah, let's begin by doing f of x and y is equal to... So this is... I should really use a different thing so it doesn't get confused with the function up above. I'll do capital F. I'll probably forget and need to go back at some point to correct that. So I'm going to say that that is equal to that plus this. Okay. I'm not saying that this is true. I'm just saying that it equals this thing. Now, I'm going to find h of this. H of f of x h of f of x, comma y. And I'm going to substitute this in to our definition of h of f of x, comma y. So this is going to be equal to this. Okay, and now, don't want to have that. Okay, and now, what am I going to do from here? Well, I can just substitute in my definition of f of x and y. I don't want to bother writing this out on a new line, so I'm just going to do it here. Firstly, we know that this, we've already shown that the plus c will come out at the end. So I'm just going to not bother adding the plus c in everywhere because we know it's going to come out at the end. And that's going to be a minus sign there. So I'm just going to substitute this in. Okay, so this is going to be inside anything inside this bracket is going to be plus w. Okay, and anything inside this bracket is going to be y plus w. Let's put that in brackets. There we are. Okay, and I'm just going to expand those out because those brackets were just there to help keep track of stuff. But I can now note, I can now group some of the following terms together. I can group these terms together. I can group this term with them, and I can note that this is equal to itself, but that first term is by definition, by the definition of the h function, is going to be equal to this. But we defined g such that was 0. So that's then will come down and be equal to this. And we can then take another closer look at this and realise that up to a factor of w that is now deeply, deeply troubling me, or up to a factor of w squared. Oh, I know what's happened. I should have... I simplified this down actually a little too far. Maybe this saves this. Maybe this isn't a disproof. I hope it isn't a disproof, because if this does turn out to be an inconsistent equation, then I've wasted a lot of time on what might have just been a troll. And this looks like it isn't. It looks like I have messed up here. So I'm going to cancel my x squareds, which, I mean, I am doing this maths relatively quickly, so I'm willing to believe I could have messed up on my logic down below. And so we're just going to leave it with this. Going to be a little more cautious now as I run through. This is then going to give me yeah, I think I messed up earlier. I don't know whether or not me messing up will mean that this doesn't work. Regardless, I'm proving a property about G. That can't be a bad thing given we've assumed G is our solution. So that can only be on the track to a right answer. This just might not be a disproof. In fact, it's looking less and less like one. Because normally we'd have an extra w squared in here. But we'll see. We'll see. It may turn out that it actually makes no impact on this solution, which I think might be the case. But we'll see. Okay, so I'm gonna... What am I going to do? I will expand out these, drop the a in here, drop an a in there, do the same here, possibly unnecessary. Don't know exactly what I'm going to do. I am kind of winging this, as may or may not be totally obvious. Okay, I'm then going to pull my AW squareds together. And this is looking concerningly like it will simply prove to be consistent. But we'll see what happens. I'm not going to give up on this just yet. Okay, so I'm going to pull the two terms together here into that. All right. Then what do we have? I find it interesting that we have these x squared still left over. That interests me. So I'm now going to, again, go down and pull out our w squared. Oh no, those will cancel. I should trust me. Oh no, I see what's going to happen. We are just going to prove this is consistent. I so thought I'd actually made some progress on this problem, but no, it would appear not. So I'm going to take this, brackets, expand, remove the half. Okay, what do I want to do from here? I want to expand this out, I think. Just try to do this whilst keeping it ideally as neat as is possible. Oh, I also need to drop that there, drop that 2A out here. Okay, and cancels to give an A from, okay, I'm just double checking that my logic does hold. Where did the 2A in front of the W squared come from? That W squared disappeared. The 2A in front of the W squared come from the AW squared in this term and the AW squared in that term. Okay, so that is all correct, and those are then cancelling off those halves we see down there, which is good. That's all right. Okay, and then I guess I just expand this term out. Alright, just pull this in. I'm not going to expand it entirely just yet. Actually, I will. Drop the A in there. Drop the A in there. Okay, and we can then see this term here. It's going to cancel with this term here. Okay, now I can expand out. I can't believe this came to just being consistent in the end, but this still might be interesting. It still might be interesting, it still might be useful. So what I'm going to show, then, I'm going to take this, I'm going to say that x squared plus 2xy plus y squared, that's just equal to that expanded out. Okay, and I'm now going to cancel the x squareds and the y squareds. I think this was what I originally intended to show. I just mucked up the maths, I think. I'd say I'm going to cancel these two, this term with the term on the right. It's equal to A plus C. Alright. This was what I think I originally wanted to show. But I messed up. Now, let A equal minus C. This is not what I was going for, but this works. If I let A equal minus C, then F equals this, I guess. I can chuck a -1 in there. Right? Yeah. If A equals minus C, we can substitute that into this equation above. So if A equals minus C, we've then got minus C plus C, that equals 0. Therefore, when and only when A equals minus C, which we've just substituted in down here, H of F is 0, and therefore F is a solution. Therefore, for any g of x and y that is a solution, there exists a second solution, f of x and y, which is made by adding this extra term on. But what does that mean? Well, let's consider the point at 0, 0. Let us say that g of y, well, let's just substitute 0, 0 into this. Because we wanted to find the solution to an equation which had that at 0, 0. We wanted to find. We have shown that both g and f obey this equation up above. However, we've also shown that they're not equal, because we can have this factor a doesn't have to be 0, so we can show that we're going to have this term separating them. But they both fit this equation. Therefore, there are multiple solutions to f of 0, 0. There is no single fixed solution to this problem. That is me breathing a sigh of relief. Fairly certain this proof holds, but obviously last time I attempted to do a proof, I also made a mistake. I didn't need to use any of this, and in fact using some of that was what led to that mistake. So let's just go up. So do I want to try once more and prove this all in one go? I feel I should. So, okay, one final time I'm going to prove everything that I use along the way. But I'm going to just use this as a trial solution and show that it does what I want it to do. Because, like, I found it. I don't have to... In order for this to be a valid proof, I don't have to show why I picked this solution. I just have to show that this exists. Alright, so let's delete... Let's save this. And let's say this. Okay, so we're going to... So I'm actually just going to start by saying this is true. Okay, and I'm going to prove that as I go. I'll prove this as I go. Okay. I think this is all the information I want and need to solve this problem. So, let us assume that we have a function g of x and y, which is a solution to this problem. Let us define the function h of g, or of some, let's call it capital F. Yeah, so capital F of x and y, and say that that is equal to this. All right. Okay. Now what we're going to do is... Oh, well. No, that's not even what I want it to be equal to. I'm talking nonsense. I'm going to say it's equal to that. Now, note what it means for this. Now it's going to see what it means for this to be equal to 0. What it means for that to be equal to 0 is that... I don't know the easiest way of getting an imply symbol here. Let's design... Come on, give me an implies. No, I need to go arrows, I guess. That statement, it's long. It did say long, double arrow. That's more like it. That implies that this is equal to 0, which in turn implies this is the case. Therefore, if we find some function such that h of that function is equal to 0, that implies that that function satisfies our conditions given above. Okay. Next step. Let's do this slightly differently from how I did it before. I'm going to consider the following function. f of... Oh, no, that's not worth it. That's not worth it. I'm just going to... So, I'm also going to delete this line because it's fairly obvious that h of x equals 0 implies that we have a solution. Given that is literally how we defined it. Okay, so what do I now want to do? I think I now literally just want to say, what is h of f of x, comma y? And I take this, drop that in here, but substitute in a lowercase f. Then I'm going to substitute. I feel we can make the step to just substituting this, and I feel this isn't too bad of a step. Oh, wait, no, oh, well, if I do it like that, it will be, because I'm bad. Here we are. Okay, so I'm going to now pull in that minus sign, plus minus that, minus that. I'm going to expand out these brackets. I'm going to try and do my working a little bit more slowly this time, given this is the final solution. And I'm then going to do the same here. I'm going to take f of x plus w, comma y, plus w, comma y, and again x plus w, comma y. Take those, again, expand out brackets, and I'm going to do the same thing again. So everything within these brackets is now going to have y set to y plus w, or y replaced with. Now, if this weren't a video, if this were a paper, I might want to use some... Well, honestly, if this were a paper, I would just substitute it in, because it's not too bad to see. Okay. Now, what I'm going to state, or I'm not going to state, we've already assumed that g of x is a solution to this equation. So what I'm now going to do is, actually, I'll keep putting these on new lines. Going to pull this minus g of x and y. Okay, that's next to that. That's next to that. Okay, and we're now going to see that, hey, this is the left-hand side of that. So I'm going to substitute. So, yeah, sorry, this in particular is equal to this, which is therefore equal to this, which means I can therefore substitute this in. And hey, g of x, comma y minus g of x, comma y. Brilliant. We're now left with this equation. I can take this x squared, I can cancel it with this x squared. Take this y squared, cancel it with this y squared. That's then going to be plus a. Really hoping I'm not mucking up as I go along. Because I have done this math so many times now. Well, not this particular maths, but I've been working with this equation for quite a long time at the moment. I've not been working on this proof for that long, but I've still been working on this as a whole. Okay, this is going to be equal to... Did I muck up last time? No. I couldn't possibly muck up. I wouldn't do something like that. Okay, now I'm going to expand this out. So we're going to get y squared plus 2yw plus w squared. Delete that. And I'm going to do the same with this. Do I want to do that, actually? I don't think I do. That made sense before when I had w squared to hand, but now I don't have w squared to hand. It makes sense to just do this. Substitute w, substitute w. Now notice that this, I'm going to go through this in a little more detail than I have every other time, just so it's clear what it is I'm doing and why I'm doing that. So I'm expanding out these brackets so they both have a minus sign in front of them. And now we're going to have 2x over 2. 2x over 2 is going to mean I'm chucking a 2x up there. And that's going to... That was a plus sign, right? Yeah. It's going to cancel with that. We're just going to be left with x. We can do the same thing over here. I'm going to check. Well, yeah, I'm just going to do the same thing. Okay. Now I want to expand this out. concerned somewhat by some of the factors. You can tell I'm really, really doubting myself, because I know I have already mucked up multiple times when trying to do this. I'm trying to solve this problem. Okay, I'm going to note here that these two brackets are exactly the same. They just have X and Y interchanged. Therefore, I'm only going to expand these out once. Okay, I'm just going to expand it out once and then just interchange X and Y, because those brackets were identical when you interchanged X and Y. So therefore, I can. And that will make my life a little bit simpler. Okay, so we're going to get, I don't know why I necessarily wrote that out in full. We're going to get this, we're going to get 2 of that, and we're going to get that. That's going to be that bracket. Okay, and we're going to have this all over again. Just, I'm going to swap every occurrence of X and Y. Let's add that on. So I'm going to swap every occurrence of X and Y. Well, this one, it doesn't matter if I swap, because, well, I'll do it. Y, X, Y, X, Y, and X. Okay. We're now going to look at this for a second. We're going to realise, yeah, that really does make no difference, because, well, okay, this is squared, -1. Wow, I can't believe I'm showing this in this much precision, but yeah, -1 squared. So I'm now going to move that -1 inside this square. Okay, I'm going to get that. I'm going to expand out that bracket, so that's going to look like that. Hey presto. We've got that. We're subtracting that. That's exactly the same as our term out front. So we have that. Okay, and we can do the same again for exactly the same reasons. We can do it up here, or if you prefer, we can do it up there, because these are both identical up to swapping the signs, up to swapping the X and Y rather. Okay, and then we can look at these two terms. I'm going to do something telling. I'm going to pull that minus sign out front, and I'm going to rewrite this as -x plus y. Note then, this term has an, okay, I'll be even more precise about it. I will expand that into both of those. Expand this out. Okay, now let's pull this to the front, and we can see, hey, these two terms are exactly the same and are being subtracted from one another. Let's delete them. And we look at this and we see, okay, this isn't equal to 0. Oh wait, pranked, it actually is. You can tell I'm getting sarcastic now. I've been working this problem for a long time. So, sorry, that's A, therefore it's 4A over A. And hey, we've got 2A plus 2A minus 4A. That's equal to 0. Hence, we have shown that this isn't in LaTeX, so I'm not gonna. Or I have a LaTeX-like font for Word, but I don't have it on this particular document. Anyway, hence we have shown that if we have f of x following this definition up above, that it is equal to 0. Hence, if there exists a single solution, g of x and y, then that implies the existence, if g of x of y equals 0, that implies, or sorry, okay, if h of g of x and y equals 0, that implies that h of g, so that h of f of x, y is equal to 0, which implies that if g is a solution, h is a solution. Therefore, if we have a solution for the function at 0, 0, we know that another solution must be given. Yeah, so let's now consider f at 0, 0. Well, that's going to be equal to g at 0, 0 plus something. So let's substitute in 0, 0, so those both disappear. Pull out this -1. And there we have it. That is our proof that there exists no solution, no unique solution to f for this equation. Because no matter what we do, we can always add this term on. And this term is not 0 at the origin, therefore there is no unique solution which is 0 at the origin. Or, sorry, there is no unique solution at the origin, sorry. Unfortunately, I could stop here. However, I haven't proven whether or not a solution can exist. This assumes there are two different things this could show. This could show either that f of 0, 0 can be anything, or it could show that there exists no value for f of 0, 0. Because this proof assumes that we have a solution. And it says that if we have a solution, then an infinite number of solutions exist. I mean, an infinite number of solutions exist at the origin. That also implies an infinite number of solutions exist. Well, you can show that implies an infinite number of solutions exist locally to the origin, I'm fairly certain. I suspect you could use that to show that an infinite number of solutions exist within a small disk surrounding the origin, and you could then... yeah, I suspect you could transform this into a differential equation. I'm not going to. Or partial differential equation, rather. I'm not going to do that. The question, then, the only question remaining, is whether or not there can be a solution. Whether or not such a solution does actually exist. And I said I wasn't going to do this. But I wonder if I wonder if I can. So this solution doesn't necessarily have to hold everywhere. So for instance, this solution can go to infinity past a certain point. I'm wondering if I can write a Taylor series for this about the origin. For a function satisfying this in terms of its value at the origin. I'm going to try this. I'm going to set... No, I don't think I can. If I could show that the solution had... Oh, no, I don't need to. Do I need to show that? So I did show something about this earlier. I've shown this previously, that you can see when w, we can find w when x and y are both equal to 0. It's going to get this, it's going to get square root 2 over 2. Hence, this at 0 is going to be equal to this, some finite distance away. And as it happens, this finite distance is going to be a square root of 2 away. Let's just, well, no, it's actually not going to be a square root of 2 away. Because that's not how, well, okay. Depends on words. Okay, what I guess I could try and do, I think I probably have done this, but what is this at the point square root of 2, square root of 2? And does it matter what it is at that point? I don't remember. That's going to be equal to 0. does this just come out to be 0? If this just comes out to be 0, then that's interesting. Because that is just square root of 2. Square root of 2 halved added to itself. W comes out to be 0. Therefore, if I evaluate this... Oh, no, I've already done that, and that didn't give me anything useful. That just gives me that this function is 0 at the square root, or 0 or infinity, or undefined at that point. We later found that if it was defined at that point, that its gradient could be any number of things around that point. And unfortunately, that makes perfect sense for what we've shown, especially if it is some sort of continuous function. So I'm not certain how much more I can show, how much closer I can get to showing whether or not, like, I've already answered the question that was posed to me, which is what is the solution. The solution is it is any number, or potentially none of them. I realise those are two quite different things, but the solution is there is not a unique solution. Sorry, I didn't mean to do that. Okay, what I'm going to consider now is I'm going to consider these at a point. And this is going to be a very particular point. Let's say W0 as well. It's going to be a very, very particular point. It's going to be a point such that this is equal to 0. It's going to be the root of the function. What I'm hoping I can do is show some properties about the root of this function. In particular, I'm hoping maybe I won't be able to. I was hoping I could show that there were 2 roots nearby, but that's not going to work. I was hoping I could show there were roots nearby, and there exists a function in mathematics which states, or there exists a proof in mathematics which states that if you can prove a... Okay, my mind is doing multiple things at once. Let's focus on one. There's a proof in mathematics that states that if a function belongs to a certain class of functions, and you know all of its zeros, and you know it doesn't go to infinity, that function is uniquely defined. Depending on what you count as doesn't go to infinity, either up to a scalar multiple or up to a multiple of e to the x, or e to the f of x rather, where f is some complex analytic function. I think that's via Strauss's theorem or something. But yeah, do I really want to prove the existence of a solution? I don't know how I would go about proving the existence of a solution. I'm amazed I managed to prove that this was undefined at the origin, or that this did not have a unique solution defined at the origin. I'm genuinely quite surprised I made it that far. How would I go about showing? I think the only way yeah, I don't know. But maybe I know something useful. We know that this is a solution. No, dang it. Okay, well this... Oh wait, no! No, this potentially... No, this isn't quite a proof. I'm fairly certain that the answer is all numbers. Because, let's substitute square root of 2 over the square root of 2 into this. We know the function... The issue is we don't know the function is 0 there. We know the function is either 0 there or undefined there. So, yeah, that doesn't help too much. What we can say is that we notice this term is equal to 0, which means that no matter what the function was at the origin, it comes down to 0 at this point. Sorry, the proof, because I haven't shown it today, the proof of this is quite simple. It is that w is equal to 0. I showed that a minute ago. W is equal to 0 when this is equal to, when x and y are equal to the square root of 2 over 2. From there, it follows that this holds. Because w is 0. Again, because w is 0. W is 0. There we are. Follows that this holds. This is either A, a contradiction, depending on how you argue it, that may or may not mean infinity. A pure mathematician would argue that I assume the function was defined, and therefore it is a contradiction because it cannot equal infinity. I would say let it equal infinity. That's more or less how we define infinity, and it's people like me that are the reason the reason that mathematics has an issue with Gödel. Because you need to assume recursion in order to get, you need to assume induction to get Gödel, or of some sense anyway. I'm no expert on that. So if the function exists, then the function goes to 0 at this point. That's not even true. Because the function could exist at 0 and go to infinity at this point. Which isn't very helpful. I wonder if I can construct a function relative. I mean, I've constructed a function relative to another function. I don't know a way of proving existence here. Existence proofs are notoriously quite difficult in mathematics. One of the Millennium Prize problems at the moment is proving the existence of and smoothness of Navier-Stokes equations. This obviously not quite Navier-Stokes equations, but honestly, this is a pretty difficult equation. Obviously, this has been picked for some reason by someone, but this is a quite difficult equation to solve. And so, no, it's not Navier-Stokes, but it's non-trivial. And so I am happy. I think I cannot come up for now with a way to prove a solution exists. Or a way to prove the uniqueness of a solution. I guess what I can do, I can try and leapfrog. So I can do something like the following. I can set this as 0. I can say this is equal to a half. Say this is 0. This is 0. This is square root of 2 over 2. Because square root of 2 over 2 is what you get when you set x and y equal to 0. You can see that up in the equation above. Set this to 0. I can, without loss of generality, if there exists a solution. Well, no, this is losing generality. But I know there exists a solution. If a solution does exist, there exists a solution where this is 0. And does that tell me anything useful whatsoever? Doesn't seem like it. What if I try the same thing? If I were to try the same thing with f of x and y, I would get what, a minus a on that side, and that bracket would cancel. So I would get this and so that's potentially not a useless piece of information. I feel like feel as though if I wanted to solve this, what I would need to do is prove something about the interchangeability of x and y. Because if I can prove the interchangeability of x and y, I can begin to solve this at particular places. So I could, for instance, I could solve this here. If I could prove that x and y could be interchanged, I could solve this because this would be. And I can conjecture that this is the case. And the annoying thing is, if there is a unique solution, this definitely... Oh, wait. Can I prove this? I think I might be able to prove this is the case. Ah. No. So... I can prove this is the case if I know the gradient at the origin as a function of a. Because if I know the gradient at the origin as a function of a, or if I have some equation that describes it, then I can argue that this problem is well defined. Or that, sorry, that's not quite, well, I mean, yes. But, so there exists a problem, which is the fact that just because I know that, let's say without loss of generality, I'm just going to say this, without loss of generality, this is equal to 0, and therefore this is equal to minus a. I'm free to say that because G was just defined as a solution. It doesn't really matter which solution, and therefore this equation isn't true. But we do have this equation, which is true. Now, the thing is, if we had evidence that we would need evidence of two things. We need evidence, A, that this function is in some sense locally, well, it isn't locally well defined. Well, it could be. We'd want some argument that states this function is in some sense analytic. There is one solution for every other solution. There's one solution and you can't get from one solution to another. They don't. So basically, setting A, the suggestion is that setting A might be enough to determine the solution. If that is the case, then we've got quite a bit of information. However, I don't think it is. I don't think it's provably the case anyway. There is one last thing I can try, which is we do have some information about this problem at one point, or at least we have some information about the complex analyticity of this problem at a single point. At that point, the function is equal to 0. So we will consider this at the point I showed it a minute ago. We're going to consider it at the point square root of 2. But we can't consider at this point because we can only consider at this point assuming that the solution exists. Yeah. I'm out. I don't know a proof. I do know that there exists no unique solution. I do not have a way of proving more than that. If anyone does, and you could let me know. I think, yeah, I'm debating whether or not I want to be told an answer to this. But I think I am happy being told an answer to this. There are a couple of ways I could think of messing with this a little bit further. If we wanted to... If I wanted to okay, I've got an idea. If I wanted to prove that there exists a unique... Okay, this equation is in some strange sense linear. In that there exists... Okay, I know how to prove this, I think. Heavy on the I think. But this equation is, in some sense, somehow... Well, some sense somehow related to a linear transformation. It's not linear, but I can look at this with linear algebra, I think. Okay, so how am I going to do this? I'm going to say... I'm going to accidentally delete stuff and muck things up. Okay. I'm going to break out the delta function. The delta function... Well, yeah, honestly, if you don't know, I don't know I can really explain this. If you don't know about much about integration, I don't think I can explain this on the fly. I certainly can't explain uniqueness proofs of this, or why this shows uniqueness or anything like that. I'm good, I'm not that good. So I'm going to try and break out some linear algebra and turn this into effectively a potentially Sturm-Liouville problem. I don't know if I can manage it. But I'm basically going to... Actually, I don't think I can turn it into Sturm-Liouville, but I can turn it into a problem that exists inside of some linear vector space. I can do that. Okay, so that's not what I want to set that to, though. So I want to set that to y primed minus y minus w. So basically, all you really need to know is that this is a linear operation. I guess I maybe don't even need to write it in this form. But I'm going to do so because it helps make me feel more confident in what I'm saying and doing. And this is going to be y. It's going to be x primed. X primed minus y minus w. Basically, if you know what an integral is, this is... Okay, integrals are areas under curves. What this is this is a peak which has 0 width, but has an area of 1 underneath it, so basically it goes up infinitely high, and I've shifted it along so it is centered at the position. This is honestly isn't that hard to explain. I've shifted it, you've just got to visualize quite well. I'd shifted along, so this is a peak that is shifted along, it's got area 1 underneath it, and it's shifted along so that it has a position at x plus, or when x primed, this should be integrating over x primed, is equal to x plus w. Because delta function is defined such that this peak is at 0. So that's going to be equal to 0 when x prime is equal to x plus w, which means this will be 0 everywhere where this isn't equal to x plus w. That means I might as well just set this being equal to x plus w. I can then take this outside of the integral because it's constant everywhere. It's a constant scaling factor. If I rescale a graph, I rescale the area underneath it, and then I have the integral of the delta function, which we define the delta function by having an area of 1 underneath it. That's all fine. The issue is going to come to explaining some other stuff later on. I'm going to make this a double integral. So this is now finding an area underneath a surface. It's going to be dy primed, and take this, and I'm going to do basically the same thing again, except this is when y is equal to y primed. So it's going to be this. And I'm going to, how do I want to do this? I'm just going to copy this over and change the things I need to. So the only real change I need to make is we're basically swapping x and y. So I'm going to do y minus w. We can do x minus, well, that's not what I'm going to do. I'm going to just do minus x. There we are. And I could also, it may seem strange, but I can also write this in a similar way. It's just going to be by removing that. Now, I can pull all of these over to one side of the equation. I'm going to need to chuck a minus sign in front of that one as well. And I can, more importantly, note that if I put multiple curves on top of one another, the total area is equal to the sum of the areas underneath. It's going to be, if you don't know what I'm going on about, it's going to be getting hard to visualize at this stage, and if you do know what I'm going on about, you're already bored by me going into explaining that. But what this means is that we can combine these together linearly, and I can chuck this. You may also notice my computer is beginning to get a little laggy, because it doesn't like me working with long equations all the time, because that uses a fair amount of memory. Okay. So this is now a linear problem. Unfortunately, still don't know how to solve it. I'm also not 100% convinced in whether or not I've actually made things better. I might not have done, actually. What I could do... Yeah, okay. No, I don't think I've made things any better. What I'm going to say is that we can convert this to the following problem. Oh, great. No, I still actually can't show this. I'm getting close, but I can't show this. Okay. So I can convert this to... I don't want to do this. I can convert this to what's known as... Maybe this helps? Don't know if it does. So I could try and convert this to what's known as an eigenvalue problem. Because this is a linear... For those of you who know what eigenvalue problems are, I mean, this is a linear equation. I would not look forward to integrating anything multiplied by that. But it is a linear equation. I can do this as an eigenvalue problem. But I don't see any way that this actually helps. This just gives us another equation. It doesn't even give me a guarantee of completeness, even if I can solve this equation. So there would still be no way of proving a solution existed without actually finding one. So yeah, I'm going to say I cannot think of a way of doing this. If you do have a way of doing it that might work, give me a hint. The hint I mentioned in the description of my previous video that I received the other day regarding this problem was you can't actually see it, but the title of this document is called Binary Recursive Problem because it was suggested to be relating to the area of binary recursion in computer science. I don't personally see how I could recurse this in a useful way. I guess what I could do, and you note most of this video is just me saying I can't do it and then having an idea. What I can do, I think, is reduce the dimensionality of the problem and show that at the very least a solution exists along an axis. So I don't know. Wait a second. Okay, I know that if a solution exists, there must exist another solution which has the same answer when swapping x and y. Does that help? What I'm thinking is solving this along the line x equals y. Because we know all of the defining equations are symmetric along that line. I mean, I can just write it down and try and solve it. So if I do x equals y, I'm going to get the following. It's 2x. X equals y, so this should all be squared. So it's why we get that. Chuck that in there. Chuck that in there. Chuck this in here. If x equals... Okay, we do get something interesting here. I swear I did this last night, but I did not notice the interesting thing I've just noticed, which is we've got this, so that cancels. And this also cancels. That 2x over 2 will cancel that x. And again, we don't have any guarantees that I'm allowed to swap x and y. I could guess that I'm allowed to swap them. I could guess that I'm allowed to swap them and see whether or not I can find a solution. However, that doesn't prove or disprove the existence of one. This did get rid of every instance of w quite neatly. But I don't... The issue is this isn't even closed along that line because we leave the line later at that point. So yeah, no, I'm officially out. If you have a hint, let me know. Otherwise, I'm calling an end to this problem. I've proven that there exists no unique solution, which... Wait a second, does that... No, that doesn't. That does have analogies with. So the reason I thought to go about linear equations is that does have links to linear equations. There being no unique solution is something you get when a matrix is non-invertible. However, there are a couple of reasons why I don't think that holds as an argument here. The no unique solutions thing. Anyway, yeah, it's been my second attempt at this problem. To anyone who actually made it this far, thank you very much for watching. I've been in Shawalog, and I will see you around. Bye.